Hello and welcome to today's ASRG World webinar. ASRG stands for Automotive Security Researcher Group. Today is the 2nd of June 2021 and we are streaming from Stuttgart in Germany. Thank you for being with us. My name is Dirk Targoni and I am ASRG lead at the Stuttgart location. The Automotive Security Researcher Group is now nearly 4 years old. ASRG is a non-profit organization which provides a platform for the automotive security industry as well as related academics or organizations to share knowledge, build powerful networks, and valuable collaboration. The community is for you, and it's based on volunteer support. If you want to know more details about ASRG, please check out our webpage at www.asrg.io or send us your questions via email to hello@asrg.io or follow the links in the description below in this video. In case you have an idea for a nice project and look for partners to realize it, you would like to start your own location, you have an idea about the services that ASRG could provide, or you know a great organization which could become partner with ASRG, we are open to hear each idea you have in mind and would like to discuss how ASRG can support it. Don't hesitate and get in touch with us. So, this is enough from my side today. I'm sure you are waiting very curiously for our main presentation. Like every time, in case you have any questions during the presentation, please write it in the chat windows. After the session, we will have some more minutes for questions and answers. And now, it is my pleasure to welcome Tobias Brennich, security consultant and security tester at ESCRYPT GmbH, and Dr. Martin Moser, head of Consulting and Testing Munich at ESCRYPT GmbH. Today, they will bring to us the topic, the 7 golden rules of successful automotive security testing. I'm very excited about this topic. And now I would like to hand over to Martin and Tobias. The virtual stage is yours.
Thank you, Dirk, very much for that very nice introduction, and welcome to the audience. So today we are going to talk about the 7 golden rules of successful security testing. So how do we make life difficult for hackers is the subtitle. And before we actually start, we would, of course, shortly introduce ourselves. So the 2 presenters, my name is Martin Moser, as Dirk already said. I'm with ESCRYPT for over 9 years now, both responsible as a group leader in Munich and also the service owner for security testing worldwide. So exactly the topic we are talking about today. And then my colleague Tobias Brennich will also introduce himself very shortly.
Yes, hello, I'm Tobias Brennich. I work at ESCRYPT under Martin since 2016. I'm working as a security consultant as well as a security tester. And in this role, I've performed various penetration and security testing projects for different automotive clients on different kinds of systems. And I'm supporting Martin in his work on security testing. Thank you.
All right, thanks very much, Tobias. Then also a few very short words about our company, ESCRYPT. I guess most of you know the company. So we are a security provider for cybersecurity, in particular in the automotive domain. So been in the field for quite some time now. So we belong to the ETAS and Bosch group, a global player here in that area, and making basically both our mother companies, of course, but also other companies. So working a lot for external companies which do not belong to Bosch and making basically their product secure. We have very complete portfolio in that direction. So starting with design security, helping our customers design security in a meaningful way, enabling security with specific products, but also other solutions and services like testing services, for example, and also managing security later on in the field. Topics like key management and security infrastructures where we are active on. So far with our introduction, and now let's start directly into the topic, maybe with a short definition. So what actually is security testing? So what's the topic we're talking about today? And basically security testing, with that term, we understand the practical technical evaluation of the security measures at a target. So a target can be some kind of system like a car, can be a ECU, some backend system and so on. So it can be manifold. And we want to practically evaluate if the security measures in the target are basically doing what they are supposed to do. And the system under test can be basically either a product which is already finished, but it's of course also possible to test products which are currently under development. The goal of security testing is always the same. So we want to find flaws or vulnerabilities that can be exploited before someone else does. It makes it very expensive, of course, to fix them later on. And that's why we want to find them before any damage, any reputation damage and so on can happen. All right. The topic or the talk for today is basically structured into 7 different areas, which we will call the 7 golden rules of successful security testing. And we are jumping now right into the first rule, which is called find security holes before someone else does. So that's what I just said on the slide before. And we're going to dive a bit deeper into detail why this is important. To start, we are looking into a very short example that many of you may know because it goes back to almost 7 years now, which is the go-to-fail vulnerability from Apple. So what happened, you can see that in the code snippet on the right-hand side, in particular in the yellow line, there's some misplaced go-to-fail statement here. So there's just one line too much of go-to-fail. And the result of that is when the program code comes to that area, it just goes to the fail state, meaning that the remaining execution of the function is canceled. And then we can have a look at what this function is supposed to do. The function is supposed to verify a certificate. And in that case, we want to build up SSL, TLS connection to the server. And in that function, we are verifying the certificate of the server. Now, with that misplaced go-to-fail statement, the result is that the function always exits before the actual certificate verification is taking place, meaning that the function exits with no error code, but at the same time also the certificate has never been verified. So that, of course, then as a result enables man-in-the-middle attacks on all, in that case, untouched Macs and iOS devices that were affected by this error. And of course, that's a serious issue. Now, the question is, why did this happen? Of course, we don't know. I mean, we can speculate. So it looks very much like a copy-paste error. Could be some kind of merge error as well. Maybe even sabotage, but we don't think so, but could be. And so maybe that's a lot of speculation. We, of course, know that one thing wasn't the cause, a lack of security awareness, or at least of conceptual security awareness at Apple, because they have a well-thought security concept. You can download it on the link that's written here. So that definitely was not the issue. So that's a theory. Now, the question is, how could we have prevented that error, or at least the error from going live into the field? And that brings us directly to the area of security testing. So there's a lot of different testing methods, which we will also introduce today. And of course, there are a lot of them who are able to detect such a failure. So for example, static code analysis would have detected that there's some code that is never even executed. So that code that can be detected by static code analysis. With a manual code audit, of course, the auditor would have seen that there's something wrong here. By doing functional security testing, you would have detected that when sending a wrong certificate, the function still returns true. And also in a penetration test, of course, you would have been able to find some things out. So with proper security testing, it's very clear that this failure would have been detected. Now, what are some typical vulnerabilities or failure that can be detected or can be found out during security testing? Oops, sorry. So there's some examples here. Of course, the list is not complete, and it's never gonna be complete, but there's examples here on the slide. So for example, some open interfaces that can be detected, robustness flaws, memory overflows, buffer overflows, for example, faulty security functions, which we just seen on the slide before. So security function which is not doing what is intended for. Then misuse of cryptographic functions happens quite often. Memory leaks are a serious issue. And of course, outdated and insecure protocols, also something that happens quite often. So these are just some examples of vulnerabilities that can be found by security testing, but of course, there's many more. Now let's look shortly into the topic of regulation, because I think many of you are aware that a lot of things are ongoing at the moment in that direction, with the UNECE ahead, with also the ISO 21434 ahead. So a lot of new regulation will be coming in the automotive domain, and there have been also quite a lot of presentations on that topic within the ASRG. So I guess many of you are aware, and now we can have a look, what does the regulation say about security testing? And they're basically first looking into the UNECE. There's a couple of statements talking about security testing, and we have kind of a look at some quotations from there. So first one, in 512, the UNECE says that the approval authority or the technical service shall verify by testing of a vehicle that security measures are in place, basically. So that's the first point, which already makes clear that as part of the type approval, security testing is going to take place. Then in the second quotation here, or citation, basically talking about more about the vehicle manufacturer, so about the OEM. And the statement here is that as part of their cybersecurity management system, they have to define processes used for testing the cybersecurity of a vehicle. So here, basically, it's talking about more about the OEMs, and also quite clear from the statement that OEMs will need to do security testing. And then a last statement here from the standard. The vehicle manufacturer shall perform, prior to type approval, appropriate and sufficient testing to verify the effectiveness of the security measures implemented. So again, very clear statement that security testing is mandatory. The question now goes, of course, so we know now security testing is important, but how do we test? What do we need to do here? And here the standards are not that clear. So there are some examples mentioned here also in the ISO, like pen testing, vulnerability scanning, fuzz testing, and so on. And also more specifically, pen testing is an option for one of the requirements here. But of course, this will be worked out in more detail in the time to come and in the next versions, and also in some other documents like the ISO PAS 5112 and so on. So as a consequence, OEMs, tier ones, and authorities must be prepared for this. So that's quite clear. And they basically need a clear security testing strategy in order to tackle these challenges and in order to deal with this. Now, summarizing our first rule. So why do we need to find security holes before someone else does? Of course, it's much more expensive to fix vulnerabilities in the field, and they can cause significant damage to reputation, financial damage as well, and even more severe damage to safety. So that's why it's important to fix them beforehand. And to find them by security testing is very important. So security testing helps you to find the vulnerabilities yourself. Thereby, of course, it helps to save costs. That's clear. And in the end, taking all together, it helps you to provide a reliable and secure product if you follow certain rules in terms of security testing. Now, let's jump into the second rule. Second rule says follow a holistic approach. So what does that mean? Basically, it means that security testing is not something that you do just at one point in time. So not a singular activity, but it basically accompanies you through the complete development and operation of the vehicles. I will show that here on the development cycle that we are seeing here. And of course, there's some activities that can already be done independent of a concrete product development. For example, defining a security testing strategy. So that can be done independently, but of course, continuous consulting of the organization, examples like security testing trainings and workshops for developers, for testers, and so on, make a lot of sense and are not depending on a concrete product. Now, when a concrete product is starting to be developed, we're typically starting with the analysis phase. And here it makes sense to define the security environment that is relevant for security testing activities later on. So for example, defining security goals, assets, impacts, and so on. And of course, the ISO 21434 CAL identification can be one part of that. Then we can move on to the design phase. Here it makes sense to create security testing concepts that basically describe the test setup, the methods and the tools that are being used. And at this stage also it makes sense in some contexts to also already test and evaluate third-party components. So if that is a major criteria for selecting third-party components, that you also look into the security, it can make sense to already test them at that stage before deciding which component to select and integrate. In the specification phase, so some typical activities in terms of security testing here are specification of functional security test cases, also specification for automated tests. So these are kind of activities that happen in specification phase. Then moving on to implementation, there, in particular, automated testing methods play a role. So there, basically, you want to continuously test single components which are under development. And some examples applying here are functional testing, code analysis, vulnerability scanning, and so on. Then we have a dedicated testing phase, but here it is very important for me to stress out that nowadays developments are very agile. And that means it's not the case that there's an implementation phase and then it ends and then there's a testing phase, but there's a lot of iteration between the two. So implementing, then testing, then implementing again, and so on. And so that's why this circular relationship here is very important for me. But in the testing phase, of course, many more security testing methods apply. We will all introduce them later on, like code analysis, functional testing, systematic fuzzing, vulnerability scanning, penetration testing, and side channel attacks. After basically development is concluded, we are going into production. So here it's quite important that security testing of the production environment can be done if, in particular, security relevant activities are taking place here. So for example, provisioning with certificates or keys in the production. Of course, we need security here as well. And then during operation, of course, continuous retesting can be applied, in particular if there's some updates which are being rolled out, but also if, for example, new attack methods are becoming public. So these are things that can be done during operation and then lead to retesting of new developments. In the phase of phases out phase, finally, security testing is not that relevant anymore. Then a short excursion to the question, so what's better, automated testing or manual testing by experts? So starting with automated testing, here we distinguish between undirected automated testing. So these are basically, say, dumb tools that can be applied to any system. They can find well-known vulnerabilities in well-known environments, so they provide a high coverage. You can use them to test continuously, repetitively, in particular in agile developments, and that in the end helps you to find vulnerabilities early and fix them early. So that's a benefit. Directed automated tests are now more specifically adopted to the target. So one example is functional tests, which are written specifically for one target. They help you to find logical vulnerabilities as well. So that's another advantage adding on to the undirected automated tests, and therefore they are more efficient for a specific target. But of course, the disadvantage is here that you need adaptation efforts. So it's more effort to develop the tests and to use the tests. Now comparing that to manual security testing, so here an expert is doing the security test. Of course, the expert is able to use tools as well, but for the experts, the tools are only the starting point and not the end of the work. And therefore, of course, the security tester can find previously unknown vulnerabilities. In particular, can also find logical errors. He can also link multiple flaws, which may be harmless individually, to complex attack paths. So this is also an advantage here. And of course, the expert can adapt all the attacks to customer-specific environments and implementations. Summing that up, to our view, all of these methods and basically approaches have their pros and cons, and that's why we think that the combination of all of those is basically gives you the best trade-off between cost efficiency on the one hand by testing automatically with tools, but security on the other hand by experts also finding flaws and vulnerabilities that tools cannot find. So summing up rule number 2, costs can be saved by carrying out security tests in the early development phase of the product. I think that became clear. Security testing is a complex issue and can include all technical systems involved and around the product, and can take place through the complete development and later on the operation lifecycle and through the complete supply chain. And last but not least, of course, automated security testing should always be part of the process, but it needs to be complemented by expert testing, by manual testing through experts. Then now we directly start into rule number 3. The more information, the more efficient. What does that mean for security testing? Starting here with a kind of a short comic. So some discussion between some kind of tester and his customer. And basically the tester is telling the customer, hey, I found that cool vulnerability. And the customer states, yeah, I already knew that, so that's nothing new for me. And the tester asks, why didn't you tell me? And the customer asks, because I wanted to do a black box test to find out, so how would a real attacker do that? And so the question that arises here is that really meaningful? So basically the customer here is paying the tester to find out things he already knows. I mean, of course, it's his choice to do so, but the question is that really meaningful? And that directly brings us to the question of black box, gray box, white box testing. So in black box testing, public information and external monitoring is possible. So that's the black box. And by doing that, of course, the efficiency is quite low. So there's a lot of time from the tester spent on reverse engineering, on information gathering, on finding out things that are already known on the other side. In comparison, in white box testing, specifications, documentation, configuration, even the source code, shell access. So a lot of more information is available to the tester. And that, of course, makes it highly efficient because time is spent on actual testing, on looking for vulnerabilities, and time is not spent on reverse engineering. Gray box then is something in between. So partial information is available, but not full information is available. So from that, I think it's quite clear that the recommendation should always be go for white box because it's more efficient. So with the same efforts, the same money, you will find more vulnerabilities and make the product more secure. But of course, on the other hand, the black box approach has lower legal and organizational boundaries, in particular when multiple parties are involved, like, for example, the OEM, the tier 1s, the tier 2s. So that makes it harder to share information. So there's boundaries. And that's why, of course, black box testing makes sense in such cases where information is not available. And in practice, of course, gray box testing is a compromise that is often used. But just the takeaway note, whenever possible, try to go for as much white box as possible. All right, so that summarizes the third rule. The more information, the more efficient the testing will be, and the more you basically get for the same efforts, and the more secure the product will be in the end. All right, so with saying that, I will hand over to my colleague Tobias now for rule number 4. Tobias, go ahead.
Thank you, Martin. Okay, let's continue with rule number 4. Decide wisely how to test. So in this rule, we will introduce you into our categorization of security testing methods. We at ASRG-WORLD like to categorize security testing into 6 different categories. This is not necessarily a golden rule or an absolute statement. In different people categorize security testing differently. In some circumstances, even we might do so. But as a general rule, we can use this categorization. We find it works quite well in practice. So these 6 categories are penetration testing, functional security testing, vulnerability scanning, fuzzing, code analysis, and hardware and side channel attacks. In the next few minutes, I will introduce you to them one by one. So starting with functional security testing. In functional security testing, your goal is to evaluate specific security features like authentication mechanisms, encryption algorithms, or integrity measures specifically. The goal here is to test for correctness of implementation, specification compliance, robustness against attacks, or to generally evaluate their performance. On the right side here, you see a graphic which should highlight this or visualize it to some extent. On the left side, you see generic valid test cases. Let's take our example from the beginning, the go to fail. That would be you send a valid, legitimate certificate and the OpenSSL software should accept it. And you can establish your OpenSSL connection. So that's a valid test case. But in functional security testing, that's not enough. You want to make sure that you test what an attacker could purposefully do to your system with intent to break it. In the example earlier, that would be that you check the individual fields in your certificate, which you have to validate, and manipulate them. And your target system should then no longer accept these certificates. So you need to test this specifically. In some circumstances, you might also try to test whether you can trick the target to accept self-signed certificates. And you can also go into a different direction. We had it that a target would not accept the certificate itself, but it would keep the non-invalid certificate in memory. And every time we sent a new certificate, it would allocate more memory for certificates until there was no more memory left and the system crashed. So this would be going towards performance robustness testing. So there's a lot you can do in functional security testing, and you definitely need to consider it. Important conditions in functional security testing are that when you define your test cases, you must work as independent from the implementation team as possible. This is not necessarily fully true for unit testing, but it's definitely true for most of the other forms of functional security testing. As I already mentioned, unit testing, in principle, functional security testing is quite similar to conventional functional testing. The important point here really is in functional security testing that we must add explicit misbehavior test cases, like the invalid inputs I mentioned earlier. And in the creation of these, you really need the mindset and view of an attacker. In other words, a security expert. However, once you set up the test cases and the test procedure, it may very well be possible that you execute these tests as part of a conventional functional testing, and then you don't need the dedicated security expert anymore during the test execution. Maybe you need them again during result evaluation, but not during the execution itself. So general preconditions in functional security testing are you have to define your test cases, which you can do based on function specifications and security goals, as mentioned earlier, independently from the implementation team, ideally. Or you can also derive your test cases from a security concept. This leads us to our next security testing method, vulnerability scanning. Vulnerability scanning is a very prominent security testing method. It's very well established in conventional IT. The basic concept is quite simple. It's a tool which scans a target for common and well-known security weaknesses. This, of course, has a major precondition that these vulnerabilities must be known ahead. for example, in form of a database like the Common Vulnerabilities and Exposure, CVE. Having such a database available, this is basically, if your target is sensitive to one of these attacks in these databases, it means these databases are a manual of attacking your targets. So you can really see vulnerability scanning as a method to prevent low-hanging fruits. Because not only you can perform vulnerability scanning, the attacker you want to protect yourself from can do it too. So if your vulnerability scanning is applicable to your system, it's almost a must to execute it. Being an automated method is, of course, very well suited for continuous integration into your development. I mentioned earlier applicability of vulnerability scanning. This is because vulnerability scanning for now has a very strong focus on classical IT environments, like conventional operating systems like Linux or Windows, or conventional network technologies like Ethernet, OpenSSL, general SSL, TLS. And niche environments like or automotive technologies are seldomly supported for now. This may change in the future, but that's how it currently is. However, of course, current trends in the automotive domain like adaptive AUTOSAR will lead to further integration of classic IT technology into automotive ECUs, automotive systems, and with this, vulnerability scanning gets more and more relevance in the automotive industry too. In vulnerability scanning, we can differentiate 3 different kinds of vulnerability scanners. What most people have in mind when they hear vulnerability scanning is the first category here, network scanners. A network scanner is also what was depicted on the graphic on the previous page. It's when you have your target connected to a network and you have your test setup connected to the same network. You execute the vulnerability scanner on this network and you look for possible vulnerabilities in the target which are reachable from the outside, like open ports, known bugs in protocols, etc. Another type of vulnerability scanner is web application scanners. Web application scanners are explicitly for web pages or web servers, which means embedded of a limited applicability. They may be relevant for common IT devices which provide a web interface. Automobiles seldomly do that. So in automobile industries, they're probably not that important at the moment. What may be relevant, however, for ECUs which implement conventional operating systems may be host-based scanners. A host-based scanner is a software which you integrate into your system. It's like a regular piece of software you can execute in your operating system. And it runs on this host system and evaluates the configuration of the system, whether there are any well-known, documented possible security issues. Those such scanners are available for common operating systems like Linux or Windows. And for conventional automotive environments, they don't really exist yet. But in infotainment systems, they may be very relevant. These host-based scanners here, you have to consider when you execute them. So you can execute them with generic user rights, which would be a black box test, or you can also execute them in a privileged mode, which would be a white box test. The next security testing method is probably my personal favorite. That's code analysis. And here you see on the picture, we have again the go to fail from the introduction. It's really a prime example of something where multiple ways of code analysis probably would have prevented this. So the basic idea of code analysis is really quite simple. You look for the problems at their root, which means you look at the code directly. And this is, of course, you would prioritize here code which is of high security relevance, like parsers, crypto implementations, communication stacks, your CAN stack, your EDS stack, everything that handles potentially hostile input. And typically, you're looking for implementation errors such as improper input validation, memory issues like buffer overflows, or logical issues. Our go-to fail here is more of a logical issue. Code analysis can happen in different ways. The primarily ones we want to look at here are static analysis and manual code audit. A quick note on dynamic program analysis. Dynamic program analysis is basically when you execute your code with some form of monitoring. You can look at the code while you execute it, run test cases like in functional testing, and look at the results, evaluate the results, which is very useful to identify runtime behavior, problems with runtime behavior. It can be seen as a form of automated debugging. However, for now, we see the most important ones as being static analysis and manual code audit. Static analysis is an automated method. It's an automated scan for formal rule violations. For this, it uses a secure coding rule set normally, like MISRA-C or CERT-C, which are already quite established in the automotive industry, and takes these rules and tries to verify whether your code keeps these rules or not. These scanners are very well suited for integration into the build chain, for example, at compile time. So it allows you to have results very quickly during development without having any experts on security involved directly. Your developer can execute these tools. In some extent, every compiler has a form of primitive static analysis already included in the form of compiler warnings. Just that dedicated static analysis tools have a much more extensive rule set. With static analysis, it may very well be feasible to actually cover your complete code base. So you don't have to select which components are of high security relevance and which aren't. You might try to just run it on all code. However, static code analysis cannot identify conceptual and logical errors. Our example from Go to Fail, this probably would have been identified as a dead code finding. However, this is not always the case. Not all programming errors cause something which violates a static analysis rule. So when it comes to conceptual and logical errors, that leads us to manual code audits. Manual code audits are performed by security experts who review the source code directly. So they don't need any setup at all. They just need some text editor in the code. And in principle, manual code audits can find all security issues which derive from the source code. These are conceptual and logical errors as well as rule violations. However, static analysis is probably more efficient when it comes to identifying those. So in the end, our recommendation would be to perform both, which enables you to find both logical flaws and technical errors. And combining both static analysis on the general code base and manual code audit on your priority, your highly critical code will give you very efficient coverage of your code. Then our next security testing method is fuzzing. Fuzzing is a testing method where you bombard an interface, communication interface, with huge amounts of randomly generated, invalid or unexpected inputs. The goal here is to trigger hidden bugs in the implementation, which may lead to insecure behavior, like information leakage, undefined behavior, or general crashes. Crashes are normally the most easy to detect failure they cause. So this figure on the right, I think, illustrates this very well. We have our target system, and in green, we have the regular communication input, which we expect. We accept it, process it, everything's fine. In purple, we have input which is clearly out of bounds for our application, so we immediately reject it. Also, no problem here. What with fuzzing we're looking for is this unexpected behavior which happens at a small edge in between green and purple. We're looking for input which is wrong, but just that much that our input validation doesn't find it, and then it can cause problems later in the system. Next slide, please. Yes. Fuzzing is a fully automated security testing method. So once it's set up, it runs automatically, which makes it very well suited for continuous integration into development. You can run fuzzing on both an individual device and a complete system network. However, you might have to pay attention to your monitoring then. You must still be able to tell which device is causing a finding. And you can run fuzzing on all kinds of targets. You can run fuzzing on a protocol like UDS, on file formats. JPEG fuzzing is quite popular in conventional IT. There's also direct source code fuzzing. Other types of fuzzing differentiations are primitive or dumb fuzzing versus smart fuzzing. A dumb fuzzer would be a fuzzer which just sends completely arbitrary input. A smart fuzzer is a fuzzer which takes the actual protocol into consideration and may as well also be stateful. Dumb smart fuzzing, there's not a hard boundary. It's more of a continuous progression towards smart fuzzing. Normally, a smart fuzzer would be more efficient. But of course, a smart fuzzer has to be purpose-built for your application and may take more effort to develop. There's also white box and black box fuzzing. This is mainly related to the form of instrumentation or target monitoring you have. In black box fuzzing, you can only monitor the external behavior of your target, whereas in white box fuzzing, you can also monitor the internal status of your target, for example, via a RAM monitor. So the next security testing method is side channel analysis or side channel attacks. Here we differentiate in two different kinds of side channel attacks. We have passive and active. In passive side channel attacks, you analyze statistically measurable information of your target, like time behavior when you input a password or power consumption while some cryptographic operation is performed. And the goal here is to extract information about the internal data handling of the system. Ideally, you want to be able to calculate cryptographic secrets, like an AES key or an RSA key. Active side channel attacks, on the other hand, also known as fault injection attacks, are aimed at manipulating the electronics during security-relevant processing operations, like power supply manipulation, clock manipulation, electromagnetic pulses, with the goal to change the execution flow or change the data while it's being processed. A classic example of this is probably the JTAG lock in a microcontroller. Typically, the JTAG lock is configured during boot by some ROM code, and if you can glitch this ROM code into taking the wrong branch during evaluation of the JTAG fuse, JTAG might be open instead of being closed. And this is not theoretical. Has been done. It's being done. So these side channel attacks are physical attacks. They go directly at the hardware of the system. So when would you want to evaluate whether your system performs side channel attacks, side channel analysis, fault injection? When did you want to perform it as a security test? And you can do this both on hardware components and on software components. For hardware components, you would want to do it, for example, to verify the effectiveness of side channel countermeasures, which are supposed to be in this hardware. Some hardware is marketed as being side channel and fault injection resilient. You might want to verify that that's actually the case. Besides having this hard, is it susceptible or not? You may want to test just how easy is it to attack a target with such kind of attacks. In many cases, you can guess it will be possible to hack the target via fault injection or side channel attacks. The question is just how much effort will it be? Is it enough to have a 300 euro hacker device, or do you need a multiple €1,000 expert setup to perform a fault injection attack? For hardware components, this may be part of component sourcing. So you should do this when you source your components, because if you find your hardware is sensitive to a form of attack, well, you already wrote all your code for it, it may be hard to change it. For software components, it's in principle not different. If you have hardened hardware, you should still harden your software, because normally it's not enough to just have a hardened hardware. You also need to write your code in a manner which is not sensitive to fault injection or side channel attacks. And if you do that, of course, you want to verify that your code is indeed working the way you intended to. This should, of course, start as early as possible during software development, because countermeasures against side channel attacks and fault injection attacks they're not easy to implement. If you find your solution doesn't work, it may be hard to change it later. And you must always consider that you have to run on real hardware. There's no point in verifying your code is not sensitive on some other hardware which may be less sensitive in itself than the one you finally run your code at. Our final security testing method is the master method, I would say, almost. It's a penetration test. Penetration testing is a practical security test from the attacker's point of view, or as some call it, authorized hacking. So here the aim is that a security expert identifies and creatively overcomes a target's defenses. This allows us to assess details not captured in conceptual analysis. So we can test the technical implementation of our theoretical security measures. We can evaluate third-party components. We can evaluate the interworking of different components. We can evaluate deviations from concept. In penetration testing usually includes a multitude of different testing methods, tools, and approaches. This can be all of the different testing methods we described earlier. They can all be executed as part of a penetration test. They can be combined. It's quite common to order a manual code audit and a penetration test together, which almost automatically makes this test into a white box pen test. It's a very efficient way of executing penetration tests. Penetration tests are always performed by highly trained security experts. That's the principal idea of a penetration test. And it complements the other security testing methods very well. It covers possible blind spots which are left by the other testing methods. It works in unknown and not well standardized environments. Like most previous methods rely on some form of tool existing ahead of time, which in penetration testing is much less the case. And penetration testing is really the only testing method which can conduct complex attacks which might combine multiple weaknesses, which in themselves may not be that critical, but combined might cause major damage to your system. And in penetration testing, you can test your target as a whole, including hardware. This concludes our rule number 4. Decide wisely how to test. It takes a high level of expertise to decide which testing method to use for every given scenario. And different methods are optimized for different fields of applications with different advantages. It's very important to choose the right methods as it leads to better results and higher efficiencies. And of course, all these testing methods are part of our extensive ESCRYPT testing portfolio. Then let's continue with rule number 5. Every component should be tested, or security is a moving target. So let's look at our future in the automotive industry to some extent already as it is today. We have vehicles on the road which communicate with all kinds of different components, backend systems. We have roadside infrastructure like these traffic lights. We have the customer devices at home. We have the manufacturing IT from the tier 1. We have backend services and enterprise IT from the OEM. We have cloud services which tie it all together. And all these are potential attack surfaces. Like manufacturing protocols may be used by an attacker to manipulate the system. The OEM protocols, it's the same. And all this must be considered in our security testing. Now let's look into the inside of our vehicle. In the vehicle, we have various kinds of components and systems. We have infotainment, which communicates with the user's smartphone. We have different chassis and comfort ECUs. We have ECU maybe controlling a rooftop window. And all of them connected via different networks. And here we have to evaluate where might an attacker want, what are attack vectors an attacker can use to enter the vehicle, what goals may he want to achieve, and what might be the small hidden things we are overlooking what an attacker might abuse. Like an obvious target is the infotainment. Here the attacker has a wireless interface. He doesn't have to open anything in the vehicle. If he can attack this and get access to the internal vehicle buses, that's very nice. So that's a critical target. However, do not forget these seemingly unimportant ECUs somewhere deep embedded into your vehicle, because maybe an attacker can use them to attack other systems in your vehicle. An ECU which is on a safety critical bus in itself, it's not important, but if an attacker can use it to break the safety systems of your vehicle, this can cause catastrophic damages. So when we want to test, we have to consider an holistic approach to our system. So this means we have to consider subcomponents like software components, hardware devices, configurations, interfaces and protocols, functions and applications. We also have to consider whole system components like backend and manufacturing applications, as we mentioned earlier, web service applications, cloud and virtual environments, mobile apps, and ECUs and ECUs compositions. And we have to consider all of our protocols. We have our conventional automotive protocols, CAN, LIN, ISOTP, UDS. In the infotainment, we have USB, more and more cellular connections. We have GPS, Bluetooth, Ethernet is entering the automotive domain, and we have Wi-Fi. Besides looking at what exactly we want to test, we also have to look a little bit at what level, at what abstraction do we test them. So there's different possible test setups. We can test, of course, on a full vehicle level, which is probably the way an attacker would, a real-world attacker would go at it. He has a car, he wants to hack it. We can also test subsystems like ECUs in a group. For example, you want to test your infotainment bus, your infotainment system as a whole with all its components, including the gateway which connects it to other systems of the vehicle. You can test individual devices, which in our case would be the ECU, which can happen with or without a REST bus simulation. But you can also test individual components like selected hardware or software components. Earlier I mentioned side channel analysis, fault injection testing on microcontrollers, hardware components. That might be a good method of testing them. You can test individual interfaces and protocols, but you can also go as low as the data level, just testing what if a certain set of data my system processes gets manipulated, what happens. So on these different test levels, you have different advantages and disadvantages. Of course, on the full vehicle level, you have the most realistic setup. It's what the attacker has at hand when he tests. You can also cover pretty much everything which is in the vehicle. It's the whole thing. However, there might be some logistical problems during testing, and probably in such a test, you will not have the same depth as if you look at individual components individually. And this is basically the trade-off you're doing. The more complex the system gets, the more realistic your setup becomes, so coverage increases, but it gets more complicated to execute the testing, and your testing depth decreases. Another topic to consider is how do you prioritize different components, different interfaces. The general recommendation here would be the most important thing are probably wireless interfaces, which do not require your attacker to have access to your vehicle in any way. These, of course, are cellular connections or any connections which are fully remote. Cellular attack might be possible from the other end of the world, but of course also Wi-Fi, Bluetooth, maybe GPS. Attacker doesn't need to enter the vehicle, gives him a greater window of opportunity. Next priority would be wired interfaces, which are easily accessible if an attacker has some access to the vehicle, like USB and SD card in the infotainment, or the diagnostic port, OBD. Following that, you might want to continue with the onboard networks, which usually will require some form of disassembly of the vehicle, some panels removed maybe in the interior or on the exterior. This would be your CAN, Ethernet, FlexRay, or LIN and MOST interfaces. These are less easy to access normally for an attacker, but they can be accessed, and if they're not protected, catastrophic damage can occur. So this would be the next priority in your testing. Finally, we have ECU internals like JTAG and debugging ports on ECUs, UARTs, memories. So these definitely need also to be considered. Finally, we have an important point, which are third-party components. How can you handle these in security testing? Like modern vehicles, we have different kind of operating systems. For example, GNU Linux in the infotainment. We have communication libraries from different sources, OpenSSL, AutoSAR stacks, hardware components from all kinds of suppliers in our ECUs. So how do we approach these? And here we give you some recommendations. For widespread open source software, like GNU Linux, OpenSSL, it's often reasonable to assume that they are already thoroughly tested. So you probably cannot contribute much in performing dedicated security testing as long as you use the latest version. However, you have to consider that you're still building your security up on trusting the community, and usually you have no proof, which may be problematic in forms of certification, type approval. Either way, you definitely have to test your individual configuration, because security of even established software is often very configuration dependent. Like simplest toy example, a GNU Linux with admin account with a trivial password is not secure, no matter how secure the system itself may be. So our recommendations would be to still perform basic vulnerability scanning, black box fuzzing, and functional security testing. For non-widespread open source software, you should treat it just as any other software in your system. If it's critical to your security, perform the full testing as you would for all other software. For commercial components, you have a few other options. Of course, you can test it yourself, but you can also ask for security testing proof from your supplier, some form of certification that he performed, for example, static analysis with this and this tool and this tool set rule set. Also, there's the option to ask the supplier to take responsibility, which can be a good option in case of less critical systems, which are not that safety critical. This concludes our rule number 5. Every component should be tested. And we hope we could show you that security testing really needs to be considered holistically on the whole system, not only holistically as in rule numbers 2 regarding the development cycle, but also holistically regarding your complete system. You need to keep in mind that an attacker will always take the easiest path to achieve his goal, and every part, aspect, component of a system has to be tested in a balanced approach. And finally, security testing can take place on all levels, from single subcomponents to complete systems and anything in between. Leads us to rule number 6. Knowledge is power, or security testing results must be properly understood and the right consequences drawn. This is basically about how do we handle findings of security testing. And so far as we know, there is no standardized process for handling of findings. So this is our recommendation. We suggest you start with a tester review. The tester takes the findings he has in his testing and rates them for criticality. And here he has 2 rating criteria, which are exploitability and the possible impact. To some of you, this may look familiar from threat and risk analysis. It follows the same principle. We have a damage that can occur by the attack, and we have how easy is this attack to be performed. Only here it's not theoretical, but practical. These findings and with criticality rating are then handed over to the developers. And the developers assess the findings fixing efforts. How difficult, how much effort is it to fix the findings? Here the priority follows of course the criticality rating. More critical findings have a higher fixing priority. However, the developer must always consider that testers make mistakes too, or they may not know enough to make a perfect rating. So the developer should always put the judgment, the criticality rating of the testers under scrutiny. And ideally, in the end, developers and testers agree on both criticality and fixing efforts, and then it's time for decision making. Based on criticality and fixing efforts, we can choose between different mitigation options. The most obvious is fixing the finding, which would cause the stop the problem. An alternative could be, if the criticality is low and the fixing efforts are high, to simply accept the finding as is, or to buy insurance from the damages. I hope you're not doing that for safety critical systems. And finally, the hardest choice probably, if criticality and fixing efforts are high, it may be required to cancel the feature altogether. In this case, as well as if you choose fixing, you need to retest. You need to confirm the finding is either not happening anymore or the function is indeed gone. The finding does not happen anymore if the function which caused it has been removed. Here, as mentioned a few times already, it's important to keep in mind that third-party components are usually difficult to fix late in development. So this cycle should happen early in development for third-party components. This already concludes rule number 6, knowledge is power. So it's really important that security testing results are properly understood and you draw the right consequences. Security experts can support you in understanding the findings and give you good advice on how to proceed. And there are multiple options how to mitigate finding, and you need to consider them carefully and based on structured criteria. With this, I will hand back to Martin, who will guide you through our last rule, number 7, and to our conclusion. Thank you.
All right, thank you very much, Tobias. So let's head directly to rule number 7. Choose your security testing partner carefully. So as security testing is increasingly becoming a standard repertoire or standard activities in terms of preventive protection and sensitive systems, of course, the question arises, who is doing the security testing? And basically on that slide here, we have listed multiple options that come into question or that are options of performing security testing, and I will quickly go through that. So starting with the development team, so actually the developers developing, for example, the ECU. Of course, they have profound knowledge of what they implemented. In particular, they know specification and they know the complete technical context here. There's definitely no communication barriers here, so a lot of advantages, of course, for the development team. But of course, we do have some challenges. So in particular, they are not independent and not neutral. And that's typically a best practice when talking about testing. So not only about security testing, but when talking about testing, that the testing should take place independently of the development. So to bring in different perspectives and to avoid that a misunderstanding from the concept or from development also transfer to a misunderstanding in writing test cases, for example. Also, typically, there's a lack of security and testing know-how in the development team, so that's another challenge. Then, of course, very often there's a dedicated testing team. So basically, the team doing the tests. They have dedicated testing competences for sure. They typically also do have a test setup or some kind of framework for testing available, so some kind of tool chain here. Challenges, so very often they are still quite close to the development team, and again here they often lack security know-how. Which brings us directly to the next possible resource for security testing, which is the security team. So I guess nowadays all OEMs, all tier 1s, tier 2s, and so on, they have dedicated security teams. And of course, they are the ones who have the expertise. So they have dedicated security expertise, also quite often security testing expertise. They can bring in independent security testing guidance and governance to the different projects. So that's basically exactly what is needed here. Challenge here is that quite often, I mean, not always, I mean, other companies around there are different, but quite often the available capacities in the security team are limited to that guidance and governance role, meaning that there's not enough capacity, not enough resources to also support concrete testing activities or concrete projects. Of course, if resources or lack of resources is a problem, that brings us to the next idea or next possible resource, which are service providers. So there are external service providers providing services, and in particular providing security testing services. So they can add in additional both expertise and additional resources to your activities. They are also independent and neutral, so that's another benefit here. Challenge, of course, complete independence comes with an additional need for communication. So the external providers, of course, are far away from the development team, and of course that provides a need for additional communication to make the information flow and to make the testing efficient. And another thing, of course, in case of, in particular, talking about white box testing, so you need to send the external provider a lot of information when you want to do white box testing. Of course, that needs a profound trust basis and trustful partnership between the parties. And the last resource listed down here is the authorities or the technical service in the new context of ISO. They will do final acceptance testing for type approval. They are definitely independent and neutral. But of course, the challenge here is that the testing is going to take place very late in the development stage. And of course, that means that when in that stage severe vulnerabilities are found, it gets very expensive to fix them. In particular, if the vulnerabilities leak back to some problems on conceptual or architectural level. So that makes it very hard to fix them at that late stage. So of course, as also Tobias stated earlier in another context, this list is not complete, and you can categorize resources differently. But it just gives an overview of who can potentially do the security testing, and of course what the pros and cons are of different parties performing the testing. And when looking shortly into the life cycle we've seen earlier, and maybe looking into the security testing artifacts that you can have and you can deal with, of course, then you need to choose carefully for which activity, for which artifact in the context of security testing, you choose which resource and basically what brings you the most benefit in terms of efficiency and in terms of security in the end to find as much vulnerabilities as possible. So concluding rule number 7, so comprehensive security testing is of course only possible if you have both the right know-how, the experts in terms of your product, in terms of your concepts and specifications, but also experts in testing and experts in security. So that's basically what you need, both from the know-how side and of course from the capacity side. And there's multiple options. And you can just choose from that what fits best to your strategy and helps you best to achieve a high security level. Now, going from rule number 7 to the summary. So in our presentation today, we have introduced 7 different rules of security testing, which we call the 7 golden rules of successful security testing, starting with finding security holes before someone else does, which is very important. And then rule number 2, we showed that a holistic approach is necessary because security testing is not a singular activity at one point in time. And rule number 3 have introduced the concept of black box and white box testing and why, of course, more information makes testing more efficient. Rule number 4, Tobias has introduced the different testing methods and which methods to apply in which situation. And rule number 5, we were talking about the different components of a vehicle and in particular his surrounding system when talking about connectivity and why it's important that all of those components are considered when talking about security testing. Rule number 6, knowledge is power. Basically now deals with what we do with the findings and what happens if we find vulnerabilities. And last but not least, rule number 7, which I just introduced, goes into detail on which testing partners and resources to use for different activities. To summarize this, security testing will pay out for you if you take it seriously. So it is essential to provide a secure product because many things can go wrong between concept and implementation. It improves the reliability and also the quality of your products. In the end, it definitely saves money because it helps you to find things earlier and avoid damage to your reputation. We've also learned that security testing becomes mandatory by the new regulation with the UNECE and the ISO 21434. will be part of type approval in future. So also the authorities will be doing security testing. We do think, and we are convinced, that the complexity of security testing can be managed if taken seriously, if taken into account early during development, and also independently on products. If you do have a dedicated security testing strategy for your specific needs, that's very important. And of course, Tobias has pointed out, there's multiple methods for security testing for different scenarios with different advantages and disadvantages. And just by using the right methods and the right tools in the right places, your security testing can become very efficient. With that said, basically, we are at the end of our presentation and are looking forward to your questions.
Yeah, Martin, Tobias, thanks a lot for the great presentation on such technical level. I really enjoyed to listen to this presentation. And now, as you said, we come to the questions. We have a question in the chat. And I assume this was for the first rule. How and when in the process does the ISO 21434 CIL affect your testing strategy?
Maybe I start.
Yeah, sure.
Since the ISO is so far not official, in the moment it doesn't affect us that much. We're working on it in the moment, how much effect we will see. In the moment it's not considered. From what we've seen so far, it will not change much in the underlying process we described in the earlier chapters in regards to security testing.
Yeah, so agreement from my side. So definitely will need to be considered as part of basically the first analysis phase, taking that into account. But it will not very much change what is done in the later stages of security testing. And as Tobias just said, so there's a lot of things ongoing here at the moment. So things are still quite in the flow. And I'm pretty sure that in the next year, things would get more concrete. And maybe also a short word about the authorities and the technical services. They are also at the moment setting up capacities, setting up know-how in that area. And so they also will define in more detail what's going on here and what's taking place in this standardization and regulation in terms of security testing, in terms of what they do actually expect from the OEMs to provide when going for type approval.
Okay, thank you. And we have another very great question. And the question is, how do you sell these good ideas to a management, especially if they cannot imagine the risk of incidents?
Yeah, that's actually a very good question. So with the risk of incidents, of course, I mean, what always helps is showing examples. I mean, the story of automotive security is maybe it was quite new, some like 10 or 15 years ago, but it's definitely not new in the year of 2021. And maybe you can just show your management a couple of real-world examples of incidents that happened and of risks that basically become real life in the future, to convince them that the issue here is not theory, but the issue is real life. So that's maybe one question, maybe one possible answer. Of course, regulation, standardization will help because it just gets more requirements which are coming directly and basically need to be fulfilled. So that basically shifts security and security testing from an optional nice to have to something which is mandatory. So that's a second thing. And of course, I mean, it depends if you're not an OEM, but if you're a supplier, tier 1, tier 2, of course, nowadays, a lot of security and security testing requirements are basically driven by the OEMs and then forwarded to suppliers, which basically also makes it mandatory or even more mandatory for the suppliers to basically take security and security testing into consideration. And maybe just one last point. I think we mentioned it in the presentation, but security testing does save money, and we are convinced about that. So this is so true in our view, and we have seen so many real-life examples where security vulnerabilities have been found just too late in the field, and we have also seen how much money that costs to fix them in that stage, and how much reputation damage that came with. So just convince your management that it saves time. And I think that's always a good argument for management.
Okay, thank you. And we just got a new question. The question is, how much using tools such as static code analysis or vulnerability analysis can be effective in the security testing? Are there specific tools recommended by standard authorities?
So far, there are no specific tools recommended as far as we know. Definitely not in the automotive domain. Generally, it depends a little bit on what your system exactly is. If you have a Linux-based system or common operating system as your target, then vulnerability scanning is probably really a really good idea, as I mentioned earlier, vulnerability scanner is almost a manual on how to hack your system. Static code analysis is always a good idea because it can find many common programming errors with relatively little investment. So it really depends. In general, we would say integrating automated tools into your development you should go for more than less if you have the choice.
Yeah, maybe a short addition from my side. So it's definitely right that there are no tools recommended by the authorities at the moment, but of course that can change. I mean, authorities are very different and heterogeneous around the world. In every country you have authorities, and of course, I cannot promise you that there's some countries in the world who already do recommend, but to our knowledge, that is not the case at the moment. What we do see from time to time is recommendations of tools from OEMs. So OEMs recommending tools to their tier 1s, tier 2s.
Prime example here would actually be static analysis with code sets like MISRA-C and Amendment 1 or CERT-C. These are actually really common.
Okay, thank you. And then I have a final question. So you spoke about 7 golden rules. So 7 is a magic number, and I like the structure, how you structured these important points. But do you have any additional recommendation for automotive security tester that are not top 7, but it is also very important to know it?
Well, I mean, of course, that talk, I mean, we could talk for 2 days here about security testing, that's for sure. So, of course, the 7 golden rules is not in anyhow like a complete statement that there's no other rules as well. I think to our mind, those 7 rules are the most important ones. So maybe just one thing which is very important to me and as a takeaway note for you, just think about security testing as early as possible and don't shift it to the later stages and saying, okay, let's do the development first, and once we're finished with development, then we're doing the testing, because then it makes it too late. It does not leave sufficient time for security testing activities. It does not leave sufficient time for basically fixing things when you have found vulnerabilities. So maybe just as a takeaway note, just consider it as early as possible.
Maybe also a tip from my side. The question was specifically what, as a security tester, you can do to improve security testing. I would say, since we're in automotive domain here, don't limit yourself to automotive. Look at what's going on in other areas. There's lots of information available which has nothing to do with automotive technology, but may still, the concept, the methods they're using may still be applicable to automotive devices.
This is a very great answer. Thank you very much. Tobias, Martin, thanks again for this great presentation and discussion. And yeah, we coming to end of our presentation. Thanks a lot for having us, for being with us, and we will see us in the next meeting again. Thank you to all. Bye-bye.
Thanks a lot to you, Dirk. Thanks a lot to the organizers and to the ASRG, and bye-bye also from my side.
Also, thanks from my side, and bye-bye.